Yeah, so before I start, I just want to thank my collaborators, Christian Hermann and Alan Weinstein, and then Alessandro Valentino. What I'll talk about today is not really directly related to research project with these people. It's more an introduction to the mathematics that I've been working with recently. And John asked me to give a slow introduction to the basics of symplectic geometry and explain a little bit the connections to Hamiltonian dynamics. So that'll be the first part. And here's the overview, the plan. So the first part is symplectic geometry in vector spaces, the linear picture dynamics, and then I'll talk about some classification problems and a tool for these, which is poset representations. Is Daniel here? I know he knows about them. Oh, and at the end, I'll try to hint at a more category-theoretic picture, which I'm excited about learning more about. Maybe you guys want to talk about that then at some point. So, I guess these things I already said. One other thing I want to mention is that a sort of theme in this talk, or a punchline at the end, is that symplectic geometry or linear geometry is connected to involutions or twisted involutions, and this is something that I'm excited about learning more about. And the idea is that symplectic structures can be thought of as fixed points in an appropriate sense with these involutions. So that's just something to keep in mind, I guess, where this is kind of going. I also want to just mention briefly some context related to the work that's been going on here. So there's been various papers studying network-like categories and functors from those categories to semantical categories that describe the behavior of these network-like systems. For example, the work on classic linear networks. And in that example, and a couple other examples, these functors, which describe then the external behavior of these systems, which were dubbed black box functors, actually land in a category where the objects are symplectic vector spaces and the morphisms are Lagrangian relations. So I'll explain a little bit also about what those definitions. So if you haven't already seen that, you'll know at the end what those objects are. And another thing maybe to mention is how I got involved with these topics. I did my master's thesis with Alan and was working on this problem of conjugation of Lagrangian relations. And at that point in time, I think he was interested in studying the linear symplectic category, so this symplectic vector spaces as objects and Lagrangian relations as morphisms, to understand the pathologies of the bad things that can happen, because the symplectic category was a term, I guess, that he coined to describe the nonlinear category, or the category where you have nonlinear symplectic objects, so symplectic manifolds and relations which are submanifolds. And this has some problems with composition, so it's not really a category. So the linear case is somehow simpler and works better, but there's still some interesting stuff going on there. And the rest of the things I listed here are more just for background for people reading the slides, just to give a sense of what kind of mathematics is maybe happening in the background. So, symplectic geometry. I tried to think first mathematically how to give a sense of the definition, and I figured everyone is familiar with Euclidean geometry. And one way to formalize Euclidean geometry is to say that we have a bilinear form on a vector space, and this is supposed to encode our notion of lengths and our notion of angles. And we make the definition that such a structure should be non-degenerate, should be symmetric, and positive definite. And the lengths and angles then are encoded by these formula that we're familiar with from elementary geometry. And a more general thing one can do is to drop the condition that it's positive definite and talk about a metric structure, which is then a bilinear form which is non-degenerate and symmetric. So such a structure comes up, for example, in Lorentzian geometry and all across mathematics, of course. And here we can still talk about length, but this length might be negative or 0. So we don't have this definite, this property. A nice thing about this definition for mathematicians is that it works over any field. So we don't need the ordering that we had for the reals. So a symplectic structure will be similar to a metric structure. We want it to be a non-degenerate bilinear form, but we'll require that it's antisymmetric instead of symmetric. And now we really don't have lengths, because when the ground field doesn't have characteristic 2, which is something we'll be avoiding at all costs always from now on, the symplectic product of a vector with itself is always 0. So this formula we had for length is not what we're looking at anymore. But there's some other interesting geometry that goes on. So these are the basic objects that we'll be looking at, vector space with a symplectic structure on it. And the isometries in this world, the maps that preserve these structures or compatible with these structures, are called Symplectic Morphisms. So everything will be linear. So if I forget the word linear, just think linear. And this is just the formula for compatibility. Sometimes I'll just say symplectic map. It's a little easier to say than symplectic morphism. So I listed a couple of facts just to give you a sense of how these spaces behave. Every symplectic vector space has to be even dimensional. And any two symplectic vector spaces of the same dimension will be symplectic morphism. So in one sense, they all kind of look the same in the same dimension. There's a certain way to get a symplectic vector space from any vector space, which is kind of a doubling construction. You take a vector space U, and you take the direct sum with the dual, and you can define this form, which I call capital omega, to emphasize that it's something special, canonical, and this is a symplectic structure then on that space. Something we won't need that much, but I'm introducing it here to set myself up to talk about mechanics examples, is the notion of a symplectic basis. This is basically a basis of your vector space, which is particularly nice. So it puts your bilinear form, the coordinate matrix of your bilinear form has a particularly simple form. So that is the block matrix form. So these are identity matrices on the antidiagonal. That's what your symplectic structure looks like with respect to this basis. Another way of thinking about symplectic structures, and one which is actually the one that will be the important way of thinking about it later on in this talk, is to think of not non-degenerate bilinear form, but think of the associated map from V to V star, which is an isomorphism by non-degeneracy. And saying that a map is a symplectic morphism is the same thing as saying that this equation holds for this tilde omega. So tilde omega is the name I give just to this map V to V star. Is everyone with me so far? You guys are very sound. You're supposed to ask questions.
So what's a classic example of a symplectic vector space? Keep in mind.
Classic example. Good question. So any two-dimensional, like R to the 2n, you can take the canonical basis and take this matrix, and it'll be symplectic. The other basic example is just doing this construction with U and U star.
Why would you take such a basis?
The symplectic basis? Well, okay, if you want to do some sort of coordinate calculations, then that's a good choice because it makes all the coordinate matrices simpler. In the mechanics examples, we'll see that these have physical meaning. So the q coordinates will be something that are generalized spatial coordinates or generalized position, and p's will be generalized momenta. So that's the next section. I'll try to explain the origins of this kind of geometry, and that's where that came from originally. That's why we also use this funny notation q and p. Okay, so yeah, here we go. So this is a bit of a very quick background sketch of how symplectic geometry arose, and arose from classical mechanics, and in particular Hamiltonian mechanics. So for those who didn't maybe study mechanics at any point, there's Newton's mechanics at the beginning when he invented calculus and wrote down his laws. And then quite a bit later, Lagrange reformulated mechanics in a different way, which was more general and more powerful, and Hamilton did a similar thing. And what I'll do now is just explain very briefly the connection between Newtonian and Hamiltonian mechanics. Lagrangian mechanics and Hamiltonian mechanics have an interesting relationship to each other, and that's more complicated. I will completely gloss over that or skip over that. So everyone knows the law F equals ma. So let's look at a simple example of a simple physical system where we have, for example, a mass m attached to a spring, like a coil spring, and if you take x to be the position coordinate, and you, for example, extend the spring and let it go, in the idealized model, this will just swing back and forth, and this motion will be described by this equation. And if we rewrite this equation, or there's like a simple trick, I guess you could say it's a trick, or just, we can rewrite this second order differential equation as a pair of first order differential equations by making this definition of these new coordinates q and p. So we just rename the position q of t, and we call the momentum mass times velocity our new coordinate p of t. And then the equations look like that. And I'll just rewrite the same equations we had as in vector notation. So we just had the change in q and the change in p as our two coordinates here at the top. And I'll go back a slide, just like the signs, the funny signs in this, on the right hand side here, I'm just encoding those now with this matrix in front, which has the structure of the canonical matrix from the symplectic form we saw before. So that's why I did the matrix, just so you can see how this is connected. And in the second line here, I'm rewriting this vector here with q and p in it as the gradient of a function q of q and p, which is defined here. And this function is called the Hamiltonian of the system. And in these basic mechanical examples, it describes the total energy of the system. So here we have kinetic energy and potential energy. And the associated equations, if I make this matrix multiplication with this vector, they look like this in blue. So the thing that's blue is highlighted because that's the usual form for what's called Hamilton's equations. On the right-hand side of this equation, I think of as a vector field, which is called the Hamiltonian vector field. So the solutions for this equation are the integral curves for this vector field. Okay, and another piece of terminology is phase space, which is a name for the set of all possible generalized positions and all possible generalized momenta. I say generalized because in many examples we're not going to be thinking of the q coordinates just as position. They can describe maybe angles, or they can describe different degrees of freedom that some complicated system can have. So this is one of the strengths of thinking more generally and abstractly about things, that we can use one mathematical formalism to describe many ways that a mechanical or physical system can have different states. So that's phase space, and in the general picture, that's modeled as a symplectic manifold or as a Poisson manifold more generally. And we're just going to stick with the vector space picture. And the sort of defining relationship between the Hamiltonian function and the Hamiltonian vector field is related by the symplectic structure. So I just wrote again the equation from before, and now in blue I've highlighted the relationship between the vector field x of h and the differential of the Hamiltonian function h. Okay, and symplectic morphisms we saw are the isomorphisms for symplectic vector spaces, and their role in the mechanical picture are two basic roles that they play. One is that they're also just basic symmetries of mechanical systems, in the sense that if you have a solution to a mechanical system and you apply such a map, then you'll also get a solution again. And the other important way that they come in is through describing the time evolution of a system. So if you give me a Hamiltonian vector field and you give me two times, t0 and t1, which should be like an initial and final state, or initial and final time, then I'll come and say, okay, I have Hamilton's equations, and I can produce for you a map, which is going to be a symplectic morphism. And this map will do what? It will take some initial point in phase space and say, this is my initial value for Hamilton's equations. Then I solve Hamilton's equations. We're going to assume that that's always possible here. And that will spit me out some curve that starts at this point, and at time 1, I'll land somewhere else, and that will give me another point in phase space. So I've gone from one point to another. That map will be a symplectic morphism. So this describes how the system evolves in time. So like in the good cases, we'll get a whole one-parameter family of symplectic morphisms. Okay, so a brief summary of the good things about Hamiltonian mechanics as opposed to Newtonian. We have a more general, abstract, and geometric framework. It also has a variational formulation. I didn't get into this, but this is connected to the principle of stationary action, and which has a lot of useful aspects to it as well. And there's a nice interplay here then between the physics and the geometry. So this, I think, something that John was speaking about recently with the Symmetries theorem. Just one aspect of nice connections between the mathematics and the physics. Another thing I thought of while trying to think of what is this all good for is the fact that when you have this nice mathematical framework, you can say a lot of things about systems without actually being able to solve them. So even if you can't solve the equations, you can prove things that make qualitative statements about a system. All right, so now I'll get back to symplectic linear algebra and set up a bit more definitions so that I can talk about the classification problems I want to talk about. So we're back in our mathematician minds, and we're in a situation where we're starting with just a symplectic vector space. And some of the basic things we can do is ask, okay, what is the notion of orthogonality? It's the same definition, you could say, as in the Euclidean case, but it behaves differently. So the orthogonal of a subspace is just the collection of vectors which are zero with respect, or when they're paired with that subspace U. And this operation of taking the orthogonal so I wrote here, it's an order reversing involution. So if you have A inside B, you take their orthogonals, and the orthogonals will be in the opposite order. And some special subspaces in the symplectic vector space are ones that behave like this with respect to this operation of taking the orthogonal. So it can be the case, for example, so if an isotropic subspace is one which is contained in its orthogonal. So unlike in orthogonal geometry, like Euclidean geometry, you have that the orthogonal of a space is always independent of the space you're taking the orthogonal of. Here, that might not be the case.
What does isotropic mean?
So isotropic, you mean this definition or
In physics,
more?
yeah.
So in physics, or in the mechanical picture I was sketching, isotropic spaces can pop up in many different ways. So one thing I could have said but didn't during the Hamiltonian picture is, for example, so maybe a small X course. Am I still? Yeah. Okay. So if you have, let's say we have our phase space, let's call it M or V, except this doesn't look very linear. And we had our Hamiltonian function, which is a function to the ground field same real numbers. And if we have a regular value of this function, then all the points in phase space, maybe I'll draw them something like this, all the points in phase space that have a constant, specifies energy will be codimension 1 surface. And the Hamiltonian vector field associated to H will be tangent to this guy. So here we have our X H. And the flow, so the solutions to Hamilton's equation will flow inside of this surface. And now, if I take some other function, called f, the r, we can also do the same construction that we did before and build. We can treat this as a Hamiltonian and mathematically and just build the vector field in the same way we build it from H. And now you can ask, okay, are these guys independent and are they orthogonal with respect to symplectic structure? And there's this notion of an integrable system or conserved quantities that are, so the system is integrable when you can find a maximal number of such functions which are mutually independent and which are, so they're commuting in the sense, so there's something called the Poisson bracket. Maybe I'm going too far afield here, but okay, so this is just the definition of the Poisson bracket. Yeah. And we say that H and F Poisson commute when this is 0, which just means that they're orthogonal. And so the functions f that commute with 8 are called integrals of motion, and when a group of them all commute with each other and with h, they'll and independent they'll span an isotropic subspace. And when a system is integrable, it has the maximal number of integrals of motion that are independent, which means that these vectors are all linear independent on an open dense subset, and maximal isotropic is the same as Lagrangian. So that's maybe one picture that appears just in the Hamiltonian picture.
It's like a subspace in which things are more free to move around or something?
Maybe not more free, but it's maybe just the natural geometric property that arises here, I guess. Maybe you have.
So like one example is that when you have this vector space with this basis of q's, so q1 through a qn, like position coordinates, q's that are momentum coordinates. Any space that's spanned by a bunch of, any space where all that's happening is that the q's are changing and the p's are all 0, so that would be isotropic. Also, anyone where all the p's are some bunch of p's get to do what they want, the q's are all fixed, those are isotropic. And then a maximal one of either of those is called Lagrangian and has half the dimension of the whole space. And so it describes, symplectic geometry describes this world in which it's very different than Euclidean geometry where all directions are sort of alike. Here, n of your two n directions can sort of get along with each other in the sense that you could treat them as being all different position coordinates. But you can't just take any old n directions and treat them all as position coordinates. And so you can take a bunch of directions and treat them as changes in position if they're isotropic. So yeah, it takes a while to get used to because it's not at all like visual geometry. Somehow the geometry is built into physics. It's a very deep and mysterious discovery if you think about it. People dreamt up this form of geometry from the point of view of just doing physics.
Good, deep and mysterious. We like deep and mysterious.
I mean, the definitions are all nice and short, but then you ask, like, what do they mean? And then that's the hard part.
Yeah, so that's good because I didn't write it out, but we heard now that Lagrangian is half-dimensional always, and the isotropic ones will be less than half, and the coisotropic ones will be more than half. There's like a dimension formula for the dimension of a subspace U plus the dimension of U orthogonal, just like in the Euclidean case. Okay, so Lagrangian relations, we wanted to talk about them. First, just we'll be doing a lot of taking of sums. So for two symplectic vector spaces, the notion of direct sum is just that we take the direct sum of the vector spaces and then the direct sum of the symplectic forms. So inside of this sum space, V prime and V are symplectic subspaces which are mutually orthogonal to each other. And if we have a symplectomorphism from V to V prime, we can look at its graph as a subspace in V plus V prime. And so we know that a symplectomorphism pulls back the form on the target to the form on the source. So if we twist, we throw in a minus sign on one of the summands. This is a new symplectic structure on V plus V prime. And with respect to this new symplectic structure, the graph of a symplectomorphism will be a Lagrangian subspace. So this is how we get the morphisms in the linear symplectic category. So a Lagrangian relation is a Lagrangian subspace in this direct sum where we twist one of the symplectic forms by multiplying it by -1. So Lagrangian relations generalize symplectomorphism because the graph of every symplectomorphism is a Lagrangian relation, but not every Lagrangian relation is the graph of the symplectomorphism. Yeah. Okay. And the general definition of a Hamiltonian vector field. So now we're getting more in the mathematical sense. So now here H had a special role because the vector field associated to it was against the dynamics of the system. Now we just want to make this procedure general, like I did for this F, and just say for any function we get a vector field by the same procedure. So we say a vector field is Hamiltonian if there exists any function H which has this defining relation via the symplectic form. And we call such a vector field linear if it's just a linear map from V to V. And a different way of saying the same thing with respect to this omega tilde map from V to V star is to say that X commutes with omega tilde in this way. So this is the adjoint map there with a minus in front. And that's the formulation I'll be using later. The symplectomorphisms from V to V, the set of all possible symplectomorphisms form a group, which we call SP V omega, and it happens to be a Lie group. And it happens to be the case also that the linear Hamiltonian vector fields correspond to the Lie algebra of this Lie group. So we call the linear Hamiltonian vector fields by this notation, the little sp v omega. And we call lag v omega the set of Lagrangian relations from V to B. Okay, so we said in the title classification problems. So here are some classification problems. One simple question is, when are two symplectic morphisms conjugate to each other? So conjugate means that we have an action by conjugation of the symplectic group on itself, and we want to know what are the orbits. We can also act with symplectic morphisms on Lagrangian relations in the same way. Symplectic morphisms are special Lagrangian relations, so we can compose here. And we can also do the same thing with linear Hamiltonian vector fields. And some basic questions are then just, can we find nice representatives for these, let's say, isomorphism classes, or these orbits? And can we give normal forms? And as is often the case in such algebraic questions, it happens to be the case that we can decompose, say, symplectic morphisms or Hamiltonian vector fields into direct sums. So we can decompose things into basic building blocks. And in good cases, these decompositions are essentially unique. So when I say essentially unique, that'll always mean if I have two decompositions, then the number of indecomposable pieces in those decompositions will be the same, and there'll be up to permutation and isomorphism between those decompositions. So the building blocks will be isomorphic. So to explain this maybe again, with an example that many people are familiar with, let's look at the classification of endomorphisms up to conjugation. So one solution to this problem, or normal forms for the solution for this, is the Jordan canonical form, for the case when the ground field is the complex numbers. So this is kind of the setup that we'll be using from now on. So I'll just go through this in this example to show you the way that I want to be thinking about this. So instead of just looking at these actions by conjugation, for a fixed V, I want to look at all possible vector spaces. So I look at a category where the objects are vector spaces together with an endomorphism. And a morphism between two such endomorphisms is a map from U to U prime, which connects the respective endomorphisms like this diagram. So when F is an isomorphism, then we have something like conjugation. So when U and U prime are the same, then this is conjugation on the nose. And yeah.
So is the endomorphism presumably something like a Hamiltonian?
Here, no. We're just looking at classifying linear maps just from U to U. We just want to know what are the basic building blocks of such a map. Yeah. And basic building blocks should be those endomorphisms that cannot be decomposed further, so the indecomposable endomorphisms. And indecomposable is meant in the sense of the natural notion of direct sum for endomorphisms. So you have two spaces with endomorphisms each, you add the spaces and you take the direct sum of the maps. And whenever I say Krull-Schmidt holds, that means that the statement for the Krull-Schmidt theorem holds for this particular case. So that means that our object, which is a vector space with an endomorphism, decomposes into decomposable pieces. So that's the first part. We have a decomposition. And the second part is that it's essentially unique. So that actually is the case for this problem. And here is a model of all of the possible indecomposable pieces, or the indecomposable objects. So they can be described using irreducible monic polynomials and integers. So this is like a parameterization of the decomposables. And when the ground field is C, normal forms for these indecomposables are the basic Jordan blocks. We have like an eigenvalue on the diagonal and ones on the upper off diagonal.
What's the Kroll-Schmidt theorem? What's the, I don't even know what the original
I think it's in
Kroll-Schmidt
group theory originally.
Oh.
But like it appears all over algebra in like various forms.
Okay.
Yeah. Yeah, and there's also something that's maybe sometimes confusing. In a lot of algebraic problems, people want to look at simple objects or irreducible objects, and that's something a little different. That means that there's no non-trivial sub-objects. Whereas here, we really want that it doesn't decompose as a sum of two objects. So that's a slight difference just to be aware of. Yeah. So the Kroll-Schmidt theorem is really about indecomposables, whereas like the Jordan and Hölder-Nurture theorem is about, or maybe I'm saying something stupid, but they're like equivalent theorems for irreducible things. Yeah. Okay, so we have three symplectic classification problems: conjugation for the symplectic group, Lagrangian relations, and Hamiltonian vector fields, which we want to think about in the same way as we did now for endomorphisms. So we look at objects which are symplectic vector spaces together with a symplectic morphism, or together with a Lagrangian relation, or together with a Hamiltonian vector field. And we have an analogous notion of direct sum. And in this case, we want the notion of isomorphism to be encoded by symplectic morphisms. And in this case, objects still decompose into indecomposables, but the essential uniqueness is a little more delicate. So it holds over complex numbers, but when you want to work with other fields, it becomes more delicate. I realized while preparing, I wasn't even sure what the situations over R. I think it's also true, but I couldn't remember why. So that's why there's a little question mark there. Something I should figure out. But mostly in the projects, or the project I was working on now, was we really just focused on the indecomposables. So like the first step of trying to understand these things is just what are the building blocks. Okay, so poset representations turned out to be a useful way to think about these problems. Basically because we can embed lots of different types of linear algebra problems into one framework. So I'll explain again sort of how this works with the endomorphism example after I give you the basic definition. So the basic setup is that we have a finite poset, which we label the elements 1 through n. And a representation of this poset in a space V will then be an n-tuple of subspaces, which are ordered in the same way as P is. So another way of saying that is that it's a monotone map from the poset to the poset of the subspaces of P. So I guess everyone's thinking functor. And the notion of isomorphism that we want for such representations. So if we have a representation in V and one in V prime, then we want a map from V to V prime, which maps each of the subspaces to the corresponding one. Okay, and such representations for a fixed P form a category. Direct sums are defined in the obvious way, and we have Kroll-Schmidt. So let's see how we can encode the endomorphism classification problem in a poset representation. So let's start with U and eta is our endomorphism on U. And we take the poset which has 4 elements and the empty order. So there's no order relations. And we look at the following 4 subspaces of U plus U. So the ambient space V is U plus U. And then we take sort of coordinate axes which are given by U. So we take U plus 0, 0 plus U, and then we take as the third subspace the graph of the identity, so the diagonal in U plus U, and then the graph of eta. And it's a simple exercise then to show that 2 such poset representations are isomorphic if and only if the corresponding endomorphisms are isomorphic.
So why is that? Oh, I'm already getting stuck. Why are there 5 things and you have a poset with 4 elements?
Because I write the ambient space first,
Okay.
and then I put a semicolon, and then the 4 guys there.
Okay.
It's just some notation.
And so none of those 4 guys ever properly contains any of the others, which is why you use this. Is that true? Which is why you use this poset with the empty order.
Yeah, except for maybe the special case where eta is the identity and the last 2 will coincide.
Okay.
Yeah. I mean,
Does that violate?
no, there's nothing wrong. But, because we're not posing.
Well, you can have more relations than. There can be more inclusion relations in your subspaces than there are in your
Yes.
ordering relations in your poset.
Yeah.
You can't do that. See how it right now.
Okay, so we want to do the same thing in the symplectic world. And we want in particular to be able to talk about these important special kinds of subspaces like isotropic subspaces, Lagrangian subspaces, symplectic subspaces. And the way we do that is, well, these subspaces are can be defined purely in terms of this involution of taking the orthogonal. And this involution is something on subspaces, the poset of subspaces of V. So we equip our poset also with an involution, which we use to encode this operation of taking the orthogonal. So we start with a poset with an order reversing involution, and we say a symplectic poset representation is then symplectic vector space together with a monotone map, which is additionally compatible with the involutions. So a simple example, how to encode an isotropic subspace. We take poset with 2 elements, and these 2 elements will correspond respectively to the subspace that's supposed to be isotropic, and then its orthogonal. So the isotropic means U is isotropic when it's contained in its orthogonal, so we associate the isotropic subspace to 1 and its orthogonal to 2. So we want this ordering that 1 is less than 2, and the fact that the poset representation respects this these involutions, of course, the encodes that it's isotropic. Okay. And in the same way as with endomorphisms, we can encode, for example, symplectic morphisms into quadruples of subspaces using symplectic representations, poset representations. So we basically do the same thing, and we take the ambient space to be V bar plus V, where V bar is the notation for V with a symplectic structure multiplied by -1. And here now, each of these spaces is a special kind of subspace. The first, V plus 0, is a symplectic subspace. 0 plus V is also symplectic, and these two are mutually orthogonal. Then the graph of the identity is a Lagrangian subspace, and so is the graph of a symplectic morphism. So to set this up, we take the poset with 4 elements, and now we want the involution to exchange the first 2 elements and leave the last 2 elements fixed. So leaving the elements fixed encodes Lagrangianity. And a similar thing can be done then for Lagrangian relations. Here we just plug in the Lagrangian relation as a subspace, and for linear Hamiltonian vector fields.
What encodes the fact that it's coming from a symplectic morphism? So so just to ask my question a bit more slowly. So that 3 perp equals 3 and 4 perp equals 4 is your way of saying that the last 2 subspaces on your list are Lagrangian. Well, what's making the last one?
So I'm not forcing, yeah, that's a good point. That's again this whole thing. So I'm not forcing these other 2 guys to be symplectic by this. But I will get a symplectic, I will get a representation that is compatible in this sense. So like, that would be imposing
It should
additional.
have just been any old Lagrangian subspace. I wanted worrying about why your fourth subspace on your list isn't just any old Lagrangian subspace instead of one of the form gamma of G.
Because I'm looking at looking at symplectic morphisms here.
We're looking at them.
I mean, I want to classify symplectic morphisms. If I wanted to,
So you're starting out knowing that G is a symplectic morphism. You're saying?
so
I was thinking that the classification of these poset reps, that nothing about the poset rep mentions directly symplectic morphism.
yeah, so there will be more. So if we just look at this poset with involution and we look at symplectic poset representations with this, there will be more than are just of this form.
Okay.
So you have to know, if you look at that whole collection, you need to know which.
Okay. So you haven't really completely reduced the problem. This other problem. You sort of, that is, you haven't solving this new problem about poset representations doesn't completely clobber the question of classifying these symplectic morphisms.
Yeah, it embeds this problem into the more general problem, but it's easy to know which ones are those because
Okay.
this is the graph of a symplectic morphism. If its intersection with these two are 0,
That's all you need?
Yep.
Oh, well then that's almost,
because
okay, well
a
that's,
Lagrangian subspace is
Right.
the graph if and only if its intersection with
Oh.
these two coordinate guys is.
so you don't have to look too much harder
Yeah.
at what you've got to tell whether it's coming close.
But that's an important point, and I guess it'll be a motivating point for what comes next, I guess, or after. So we get a category again of symplectic poset representations, again with the appropriate notion of sum, and again, as in the other symplectic situation, we have decompositions, but the essential uniqueness is more delicate. But the first basic task then is just to figure out what are the decomposables, what are the basic building blocks. And the basic strategy is to relate the symplectic poset representations to the classification of regular, ordinary poset representations. And the caveat here is just that it might not be that this category representation is well understood. But for a lot of simple posets, there's a full classification, and this is closely related to quiver representations. So there's this trichotomy of finite type, tame type, and wild type. And the finite type and the tame type ones are fully classified, and in the finite type you only have finitely many indecomposable pieces, and in the tame type you have infinitely many, but they're under control in some sense. So in those cases, if we relate these two, the symplectic poset representations with the normal poset representations, we can solve problems. So I'll delve into a little bit more theory of how these two categories relate to each other. So in order to differentiate between symplectic and ordinary poset representations, I'll call the ordinary ones linear, even if we might have an involution floating around on our poset. And if we have a symplectic poset representations, we can always forget that it's compatible with the involutions and just treat it as a linear poset representation. So I've used the notation that psi is for linear guys and phi is for symplectic guys, and I put a hat when I'm forgetting. And if we have a linear poset representation of a poset with involution, there's a notion of dual representation. So the dual representation is on V star, and we use the involution on P. So we say for an element I of the poset P, the subspace we get in V star is the one that is associated, is the annihilator of C of I perp, perp being this symbol, the involution on P. So this notion of dual involves the involution on P. And this notion of duality gives us a way to build symplectic representations, which is completely analogous to the way we built a symplectic vector space by taking U plus U star. And this is what we call symplectification. I think you guys also had symplectification in the linear networks, I think. So what we do is we take a linear representation and we do this doubling construction. So the symplectification is just psi plus psi star. And we equip the space V star plus V with a canonical symplectic form. And we call a symplectic decomposable representation split if it is isomorphic to such a symplectification. So it splits into these two pieces. And an indecomposable symplectic representation is non-split then if it's not. It's non-split if its underlying linear representation is also indecomposable. And we'll see in the next slide that these are really mutually exclusive things. So that's why we say non-split and non-split. So to clarify the second point, so in the non-split case, the situation is we have an indecomposable symplectic representation. Its underlying linear representation is indecomposable. And the fact that it came from a symplectic one means that we can find a symplectic form downstairs which is compatible with the involution in the right way to make it symplectic. So such a symplectic form will be called a compatible form. So it's compatible with the linear representation psi. And in general, there might be, for a given psi, multiple different symplectic forms that make psi into symplectic representation, which are not necessarily symplectic. Okay, so this is what I call the magic lemma, because it's somehow magic, both because it's good news that split and non-split are the only two things that can happen. So that's the statement of the lemma. And because the proof is something which is sort of magical, and this is something we found in two different places and used it for our situation. So what is the statement? Again, so if we have an indecomposable symplectic poset representation, it's either split or non-split, which means either it's the symplectification of an indecomposable linear representation, or we forget the symplectic structure and we get something indecomposable. So that's the non-split case. And the reason this is good news is that we can follow we can use the following strategy then for our classification. So this is what allows us really to easily relate the symplectic representations to the regular ones, the ordinary ones. So we can first ask ourselves, what are the linear indecomposable representations which admit a compatible symplectic structure? And if we classify all the ways that we can put a compatible symplectic structure on these guys, then that will give us all of the non-split symplectic representations. And then by this lemma, we know then that all the other guys are symplectifications. So then we're done, because we can just take all the other guys and hit them with symplectification. And we're done. So the tricky part is this thing about knowing what are all the compatible forms, and which are the indecomposable poset representations that admit such forms. And the project I was working on in this world was the classification of triples of isotropic subspaces, which was a fairly arbitrary choice of problem. It came about because we were working on this question of classifying Lagrangians up to conjugation, and a sub-problem of that is classifying tuples, or so pairs of isotropic subspaces, and then we got curious, can we do triples, and then it turned out to be a lot more complicated. But then it forced us to figure out what the general framework could be. Okay, and now after working on that stuff, I kind of thought, well, I'm interested in category theory and I don't want to be stuck in this poset world. So what are the general things going on that could be also transferred to other areas in a more general situation? So one way I think that's helpful for setting this up, and which I've also found in parts of the literature, is like this. So we make the following definition. A category with a twisted involution is a category C with a functor from C to C up, which such that we have an adjunction between, so I call this twisted involution delta, so we have an adjunction between delta and delta up. And eta here is the unit, and eta up is the code. So a simple basic example is when we have finite dimensional vector spaces, and we take delta just to be taking a dual. And on morphisms, we take the adjoint. And for the unit, we can just take the usual canonical isomorphism from V to V double dual. And an important twist or variant that we'll be using is to take the negative of the isomorphism from V to V double dual. So that will be giving us symplectic things. Using the usual one will give us symmetric things. So there's a nice interplay, which I kind of suppressed in this talk, between the symmetric world and the symplectic world. So they're really intermeshed, actually, in this whole picture, also in the poset representation world. But I'm sticking to the symplectic because I know about that more, and because I have the feeling that the symmetric world is it's more complicated, generally. But they're actually really connected, so a proper understanding is really to understand them both at the same time. Okay, another simple example is when we have a poset with twisted involution. That's another thing that gives us a twisted involutional category. Okay. And the idea now is that, as I mentioned at the very beginning, as a theme, is that symplectic things we can encode them as fixed points for an involution, a twisted involution. So the definition for a fixed point of a twisted involution is that we have a pair which is given by an object of our category C together with a morphism from that object X to the involution applied to X and then viewed back in the original category. So delta went from C to C up, but we want to take delta X then as an object in C again, and we want this morphism to have a basic compatibility with delta, which is encoded by saying that this triangle should commute. So we have here the unit of the induction. Yeah, so fixed points, I was going to say something else, but I don't remember. Oh, that for now, requiring that H is an isomorphism is what we want, but I think a lot of this stuff also works if we weaken it to just having a morphism. So the notion of a morphism between fixed points then is fairly straightforward. We want a morphism in C between the respective objects, so from X to X prime, and then we want this morphism in C to be compatible with H and H prime in the most simple way. So there we don't have a commutative square, we have H is equal to this triple composition. Contravariance comes in. Okay, so symplectic things. How does this connect? So now let's look at an example where we have finite dimensional vector spaces and the same involution as we did before, taking V star and adjoint maps. And now we look at the negative of the embedding of V into V double dual with the isomorphism in this case. And fixed points then are the same thing as symplectic structures. So why is that? Well, we said symplectic structure can be encoded by this map tilde omega from V to V star. The fact that that is an isomorphism means that we have something non-degenerate. And the fact that it's anti-symmetric is encoded by this triangle that commutes. So this is the equation for the triangle commuting. And that's saying that omega is anti-symmetric. And then morphisms of fixed points are symplectic morphisms. That's why, so this commutativity condition is the same as the condition I wrote of saying symplectic morphisms when we want to formulate it, if you remember.
So now you
Way
can say
back.
a symplectic vector space is just a fixed point of the twisted evolution
So much
on
simpler, I know.
finite dimensional vector spaces. Correct.
Should have said that at the beginning.
Well, it does, I mean, once you understand it, it does really kind of bound it.
Yeah, it's simpler in one way.
Why do you make it inevitable? Because the involution is one of the most natural and important things about vector space.
This is those weird, yeah, so the weird thing is he's using the eta, the unit of the adjunction with a minus sign stuck in. So if he then stuck in that minus one, he'd be doing a
Metric.
Yeah, metric, yeah, spaces with a non-degenerate symmetric Biot uniform. So that's a sort of sneaky feature that you can stick that minus in.
Another example is then to how we can get symplectic poset representation as fixed points. So here we can look at our base category C as being ordinary linear representations of a poset with involution, and we already have the notion of the dual representation, so that's how we define our involution. And we take the same unit again for our junction, and then we get symplectic poset representations. And the morphisms are the ones we want. And now, I guess at the end, this is maybe a way to look at some of the classification problems we looked at without embedding the rules of poset representations, but trying to treat them directly on their own with this point of view. So, for example, the classification of symplectic morphisms up to conjugation. So let's look at the base category where we have objects which are a vector space together with an invertible linear map. And we define our involution to take V together with the automorphism G and turn it into V star and G star inverted. And the unit for this adjunction will be the same as we've been using now. And then fixed points will encode symplectic morphisms. So before, I guess the point of view is we start with something symplectic and we want a map which is compatible. That's a symplectic morphism. And now we start with invertible maps and we find the form that's compatible. So it's like twisting the order of thinking a little bit. Yeah. So fixed points encode symplectic morphisms, and the morphisms of fixed points then are maps which conjugate the symplectic morphisms like we wanted for our classification problem. Okay. And another example was the linear Hamiltonian vector fields. So here we take objects which are vector spaces with an endomorphism X, which we want to make Hamiltonian, and our involution will send V together with X to V star together with minus X star. And the fixed points are the linear Hamiltonian vector fields, and the morphisms do what we want. So I'm not sure how many things one can do with this, and people have already done these kind of things a little bit. So there's this literature from some group in Germany from the 70s that were really using this kind of point of view for quadratic forms, but they're really focused on that kind of thing. It seems like one can maybe do a lot of geometric things with this point of view. It's something to be explored, I guess. Okay, so to sum up, I guess the things that I think are nice patterns and themes in this whole picture are that symplectic and the symmetric pictures, and the metric geometry is connected to involutions, twisted involutions. And another sort of general phenomenon is when we want to look at indecomposables that I think this is just basic things connected with involutions, that you have these things that are invariant under the involution, so they're non-split, and then there's things that aren't invariant, but if you pair them with their dual, then they become invariant. So these are the split things. And these non-split things can be built using some sort of systematic construction, which was simplification in this talk. And yeah, it seems like there's a lot of nice category theory bucking. All right, so that's all I have to say. I guess there's 5 minutes for questions.
Sure.
I guess.
Yeah, well, any questions?
So one of you, I think, mentioned that you felt like you had discovered something that you felt was pretty fundamental in this paper.
In which paper?
The one that y'all are finishing.
Finishing, that's a little optimistic statement. But that stuff that he and I are working on has nothing to do with this particularly, except it has to do with symplectic geometry. So I don't think I want to start talking about our chemistry and symplectic geometry.
Okay.
I have a question. So usually when you do classification theorems, you get down to some big list of possibilities, like, oh, here are all the incomposable things. So maybe because this is a category theory seminar or something or other, you seem to have dodged doing that. So that is, you never saw that kind of list. So is it because you don't have it yet, or is it because you were trying to be nice and not show it to us? Because I was like scared of it or something.
Well, it's really ugly to list that because, well, it depends on what classification
I
problem.
think it's great.
Well, it depends on what classification problem. So like,
So a warthog, another warthog, you could do. Right?
but yeah, it's not ugly, but so part of the answer is also that I don't know, like off the top of my head, a nice way to say it for certain things. I can just sort of, in a vague way, describe how you could make a list for symplectic morphisms for nice fields. So basically, I made the list for the one classification problem here with, like I'm not supposed to be eating on camera. Yeah, our list is parametrized by monic, irreducible polynomials, and integers. And these are the indecomposable pieces for endomorphism. So for the symplectic group, you'll have split and non-split things, and you'll have an involution floating around, and that involution will also appear in the polynomials. So you have a notion of the dual polynomial, and we'll have a list where you have non-split guys, which are parameterized by self-dual polynomials, and you'll have split guys, which are a direct sum of something that's listed by p times p star. So
how are polynomials getting involved in what you do?
So for the classification of endomorphisms, one way to model the indecomposable guys is looking at this vector space. I'm not supposed to be recording. This vector space. So we take polynomial algebra in one variable, and we quotient by the ideal generated by this polynomial to the nth power. And this will be a vector space. And then we look at the endomorphism mu x, which is multiplication by the variable x. So this is like a very special kind of vector space and a special kind of endomorphism. But it happens that this is a nice way to model the indecomposables for this problem.
Yeah,
so that's
I
how
guess when you're forced to learn the proof of the Jordan theorem, that's how you do it.
Yeah. So this will be the characteristic polynomial of the arid endomorphism.
So then I guess you're hinting that something similar like that shows up in this.
Yes, exactly. So like a complete list for the symplectic group, for good fields will look like this with certain extra conditions for the polynomial. So I guess it would be like a list with two parts, like the split and the non-split. And the involution for the polynomials is a nice one. Like if you think of a polynomial as a list of integers, so monopolynomial, the involution is just switch, like reflect that vector, not integers, sorry, just coefficients, thanks. Just flip that around and then normalize it so it's monic again.
Oh, that's a weird operation. That's a fun, weird operation of polynomials that we don't normally talk about. Cool.
Do you guys ever see involutions like that? Is that something that comes up?
See involutions like what?
Like the twisted involution, like something, the junctions where you have functor C to C up, which is a joint to its opposite.
Categories of cospans of natural.
Exactly.
Yeah.
Yeah, so daggers would be like a really special case of that, I guess.
Yeah. Yeah. I think the short answer is yes. So, I mean, so people like people like. So I mean, there are all these. Sorry. So. Yeah, I guess some daggers category. Yeah, anyway, I'm getting very confused, but I guess they only show up in linear contexts. So they're like.
Are these only used to compact those categories?
They have a lot to do with that. Yes, I mean, so there's lots of situations where you have a adjoint equivalence. Wait, is this what you're doing? Lots of situations where you have an adjoint equivalence between a category and its. There are not many situations, but there are where you have an adjoint equivalence between a category and its opposite. But those would tend to be linear situations, category defining dimensional vector spaces. And there are like tons more.
Well, here we also,
Yeah.
I mean, for the linear problems, we also want to be in the linear world.
Right, but yeah, well, but you were just saying like, have us category theorists ever
Is this kind of
seen them? And I realized I don't know if I've ever seen any of them except in the linear world.
Not about lots of compact closed categories. Usually they represent diagonal triplets and stuff.
Okay.
So they're not built out of linear algebra.
They're usually generated by something. So you generate the free compact closed category in this set or some special type graph. And then you do these categories. You use this stuff on those. I'm not sure.
Yeah, it'd be fun to, we should talk about that as a gang sometime and try to like come up with some stuff. But. Okay, let's thank the speaker again.